Hello, everyone, and welcome to another wonderful day of physical chemistry. So far, we've been focusing on how to build up the electron distribution around a hydrogenic atom. However, it turns out there's only so much I can really do with a single electron. So we're going to go ahead and start looking at how do things work if I've got multiple electrons. So one of the first things we should think about is how am I going to build up my wave function? Because a wave function is really kind of what the system's all about. So what we're going to do is try and define our wave function using two separate vectors. Each one will denote the position of a separate electron. So if I am dealing with n electrons, I'll have n of these different vectors. However, let's deal with the simple system where I've got two electrons, each with a simple vector. Now the bold R here is going to denote that we're working with a vector of I. So my two electron wave function is going to be a function of the position of the first electron and the position of the second electron. Now I need to try and come up with, a clever way to try and treat this system. So our first instinct should actually, and it's actually a pretty good one, is that these two electrons should theoretically have independent positions. Well, if the positions are relatively treated as independent, then this means that I should be able to build up my total wave function from a product of my individual orbitals. And because the only orbitals we really know at this point are the hydrogenic orbitals. So what we can do is say, if I've got a wave function for, say, helium, I can treat it out as the product of two hydrogenic 1s electrons. Two electrons, both sitting in the 1s orbital. I should be able to just multiply these two together. So we're going to go ahead and use this kind of test wave function to try and examine some systems. So this approximation that I can just multiply my wave functions together, no muss, no fuss, is called the orbital approximation. I can build a molecular wave function from atomic hydrogen orbitals. Don't need to modify it or anything. Things shouldn't change that much. I've already built in any changes in charge, so we should be good. Well, if I'm able to treat my wave functions as being independent and separable, this means, as we've seen previously, that I can do the same thing for my Hamiltonian. So my Hamiltonian should just be essentially the sum of my individual Hamiltonians. My Hamiltonian is separable, so is my wave function. So what's this Hamiltonian going to look like? Well, we know it has to contain certain key parts. The first of which is that it should have account for the kinetic energy of the first electron and the potential energy of the first electron. So I can describe the kinetic energy using our good old kinetic Hamiltonian, h bar squared over twice the mass times the second derivative with respect to position. The important thing here is that this position I'm taking the differential of is just going to be the position of the first electron. Similarly, I can find the potential energy of that first electron by assuming that it exists just in the presence of the nucleus. So it's going to be attracted to the nucleus, so negative potential energy based on the nuclear charge and the charge in the nucleus times the charge of the electron, all over the same things we've dealt with before. Big note here, the R here is going to be the full, is going to be the radius of that electron, of the first electron from the nucleus. And then I can repeat this whole same process for the second electron. Kinetic energy of the second electron, potential energy of the second electron. Derivative just with respect to the position of the first electron, derivative just with respect to the second electron. Position of the first, position of the second. This should give me a relatively independent set of Hamiltonians I can just add together. So what we can do is see what our energy looks like under this orbital approximation. So if I apply my Hamiltonian to this net wave function, it's going to be the same as applying the sum of my two individual Hamiltonians to the product of my two individual wave functions. And we've seen several problems similar to this before, but let's go ahead and work it out. First instinct is that I should have to distribute my wave functions or distribute my Hamiltonians. So I'll have the Hamiltonian of the with respect to position of electron 1 times the overall wave function plus the Hamiltonian with respect to electron 2 times the whole wave function. But here's where the key trick comes in. Since this Hamiltonian's just with respect to the position of electron 1, anything involving electron 2 is just a constant. It has no position of electron 1, so it can go ahead and come on forward because it's a constant. Similarly, we encountered the same behavior with electron 1 and the second part. It doesn't depend on the derivative or position of electron 2, so it can come on forward. Then I can go ahead and break this system down into its, again, simple parts. I know what the answer should be for the Hamiltonian of the first electron times the hydrogenic orbital for the first electron. It should just be the energy for that first electron. So if that's the 1s orbital, it's the energy of a 1s electron. 2s, then it's the energy of an electron in the n equals 2 state. So far, so good. We can do this. This actually is fairly straightforward. Similar thing happens with the energy of electron 2. Now we get really lucky because E is a constant. In both cases, it's a numerical energy value. So I can pull it out front. My wave functions themselves should commute. So what I have is simply the energy of electron 1 times the total wave function. So I can then pull it out, and the same thing with E2. So I can pull out my sum of energies out front and be left with just my overall wave function with of electron 1 times the wave function of electron 2. That's my total wave function. So this is a long proof just showing I apply the Hamiltonian to my wave function product, I get the total energy. But the real important part here is that my total energy is literally going to be the sum of my hydrogenic energies. So if I know the energy of any hydrogenic orbital, I combine the orbitals, orbital energies, I should get my total energy. Easy peasy, 1, 2, 3 We don't have to make any big issues of it. Unfortunately, we did neglect one important part of a multi-electron system, and this is the real doozy. It's the fact that the real system, electrons don't like each other. So I have to include a term, which is going to be a positive potential energy indicating repulsion. And it's going to be based on the product of the charge of the two electrons, again, all over 4 pi times how well charge transmits through a vacuum, times the distance between the two electrons. And this is the real pain. Because then in order to get this energy, it turns out those two wave functions aren't separable because the Hamiltonian isn't really separable. And we aren't going to find a good way to get a good eigenvalue or eigenvector for this system. So it's really messy. And in truth, I'm often going to have to settle for an expectation value, which means I've got to integrate over this Hamiltonian applied to a wave function times the complex conjugate of another wave function. The system actually gets kind of messy. So what one of the key struggles of quantum mechanics and chemistry is how to solve essentially this complex wave function. So I've got my classic 1 electron wave functions. I can sum these two all together. But I have to deal with the fact of this electron repulsion. And electron repulsion is really the hardest problem we typically encounter as quantum mechanical chemists, or in truth as chemists in general. So a lot of our efforts going to be trying to find workarounds of simple solutions of of this, and this is going to require some clever uses of wave functions and combinations thereof. So over the next couple of lectures, we're going to deal with some of the tricks of kind of combining our two systems. We're going to start with the classic Gen Chem trick of, well, what if I just neglect this and count it as an effect on the potential or on the charge of the nuclei? So next time, electron, electron shielding. Till then, take care.